happened, we started talking about this right at the end of class on Tuesday. So the graph on the left, which we'll get to your green sheets in one slide, the graph on the left says this indicates the rate of change of the amount of water in a tub in gallons per minute at time t minutes. So in other words, this graph here is not representing an amount of water. It's representing the rate of change of the volume of water, the rate of change of the volume of water in the tub. So if you can see this rate of change at time 1 looks to be 1.5. So after 1 minute from whenever I started, the rate of change is 1.5 gallons per minute. And it's still 1.5 gallons per minute if I look anywhere else on this graph. So it's a positive 1.5, correct? So is this tub being filled or being drained? It's being filled. Now, I could represent being drained at a constant rate also, but I'd have to have a different graph that had negative rate values. And again, this is a graph of the rates are the dependent values. The y values in that red graph are the rates at which the water is changing. It just happens to be one rate all the time. So our goal is to be able to look at rate graphs and understand rate functions and think about starting from a rate and trying to figure out what happens because of that. So I know how fast, in this case, the water is being added to the tub. What I want to know is how much water is in the tub, or how much water was added to the tub during a particular time interval. Questions like that. And I can figure that out if I know the rate. Just like we talked about in class, if you know how fast I'm driving, you can figure out how far I drove during a particular length of time. As long as it's a constant rate, that's pretty easy to figure out. But not everything changes at constant rates, so we're going to work on this for a little while. One other thing to keep in mind, though, there's these two different graphs to the right here. They're representing two possibilities out of infinitely many possibilities of what this rate could be representative of. Both of these on the right could represent how much water's in the tub. They both have all positive y values that could be water in the tub in, as long as we have units over here, maybe in gallons. So what's the difference here? This one is up higher than the top graph. What's the difference between these? Yeah.
The weight of bearing.
Yeah, starting point. So a starting point would mean what relative to tubs and water?
The weight of bearing.
The what was that?
The weight of bearing.
So yeah, it's related to the weight of the barrel question we had on your last quiz, but this one's just water in a tub. So this is, instead of, that question started with a barrel weighs B pounds when it's empty, and then you fill it with water. Well, this is a tub. We're not talking about the weight of it, but yeah, it could have had water in it already. Maybe it was sitting there and it got cold, so you started to add some more water to it for a while. So preferably hot water so it's not cold. But based on just looking at the rate, we don't know how much water there is altogether unless we're told a starting amount. So I could, this top graph, I could say if the tub started empty, I could say this is how much total water there is in the tub. Or, I don't know if you can see what that says there, I could also take this to just mean the number of gallons of water added to the tub since time 0. So at time 0, however much was in there, I don't care. Let me just track how much has cumulatively been added to the tub since then, which wouldn't depend on how much I started with. So I could take this to mean that. I could take it to mean it was an empty tub, and then I started adding water. Now the bottom one, the number of gallons in the tub at time t minutes, since this starts at 2 as opposed to 0, there's a little bit less wiggle room. But essentially it's just saying, oh, we're starting from 2, if this is related to that rate graph, 2 gallons of water in our tub, and it increases from there at a rate of 1.5 gallons per minute. So this is looking at a constant rate of change function, meaning constant rate of change, if I'm looking at the rate of change graph, has to be not just a straight line, but horizontal, right? A horizontal constant rate, one y value, one dependent value throughout. That's what a constant rate graph looks like when there's a constant rate. Pick the rate, that y value is the rate everywhere. So, like I said, that's not everything happens at constant rates all the time. One constant rate throughout, but we can think about this in order to have a starting point where we're going over the rest of today and then next week is looking at a rate function and generating an accumulation function. So we can do specific computations. We can look at rate values and come up with specific amounts of whatever it is, accumulating water in a tub. I've said accumulation to be a general. In this case, it's we're gaining more stuff, more water in the tub. Maybe it's money in another case. Maybe it's population. Maybe it's elevation. Could be lots of different things that we gain or lose. I'll just say accumulation in general to mean what happens because of the rate of change that we have and letting time go on, or whatever the independent variable is. So net accumulation is a phrase that just indicates, oh, we'll just based on starting at zero, based on just a particular starting point, what's happened since then, and not worrying about the initial value. It's not too much different, though, to say, okay, now I have additional information. So the top graph here, I can generate that if I say, well, let's just zero out everything. Let's just imagine we're starting with an empty tub, or imagine I just care about how much was added after time zero. This net accumulation just tracks that extra only due to the rate you see. It doesn't have to have any other information. The bottom graph, as you can see, the bottom graph requires we know extra beyond the rate. I wouldn't know anything about that magical 2 vertical intercept there, that at time zero there were 2 gallons, unless somebody told me. So I can always generate from the right sorts of relatively smooth looking rate of change functions. I can generate net accumulation functions, and with extra information I can generate something that tells me total accumulation or a total amount of something, including any starting values. So here's what you see a picture of this on your green sheet that you got. Now, there's some other things also on that side. We're going to work through them together, but it's kind of detailed, and I wanted us to all have the same physical graph so we can draw some things on it. So function R gives the rate of change of the volume of oil when there's an oil spill. We've got a rig that begins leaking at time t equals 0. And this is the rate of change of the volume of oil. So you can see the units on here. Whenever you're presented with a graph, make sure you look carefully at whether it's paragraphs around or labels on the graph. Make sure you know what are the units, what is this showing me? So it's very easy, especially we've been looking at lots of different sorts of graphs. You just drew me a graph of how much lawn was remaining to be mowed, and a constant rate of decrease was just a graph going downhill in the positive, first quadrant area. If I had a graph like this going downhill in the positive first quadrant, well, first of all, this has nothing to do with graphs and mowing. This is about oil. But this is showing me also a rate at which the oil is spilling, giving in cubic meters per day. So the bottom scale there goes from 0 through 2.5 days. Think about this for a minute, and I'll ask for volunteers in a second. What does it mean that this graph is going downward through the first quadrant? Think about what that means about this situation. Goes back upward for a little bit, but when it starts going downward, anybody describe for me what that means, that this red line-ish thing is going downward? Yeah.
So it's being drained out of pastures.
All right, so we've got oil leaking from a rig, and this is the rate in cubic meters per day at which it's leaking. So you said the rate at which it's draining?
Yeah.
Okay, so this is up near 28 or so, and then here it's at 20. what does that mean about oil leaking? Is there less oil that's leaked? There's more oil leaked? Is there less oil? What is this telling us? Is it going back in? Unleaking? No. Leaking slower. I like leaking slower. So yeah, so if you can imagine, suppose that we're just looking at this time 0. Suppose I didn't have this whole graph and I just knew there was a point on this that's at 0, 28. And say, oh, so the oil's leaking at 28 cubic meters per day. It's a lot of oil. And then I came back the next day and just found another point on the graph. And I said, oh, the oil is it's still leaking. The oil's leaking at a rate of, maybe that's about 5 cubic meters per day. So it's still leaking. And a lot of oil's leaked in the meantime between the last day when I was there, right? But it's leaking more slowly, leaking slower. So be careful about, like, it's easy to say, oh, it's going down. It is going down. What is it? This is our rate. So our rate is going down. Make sure you're careful about if you're trying to describe something, whether it's to somebody else or just inside your own head. Or, as I suggest, talk out loud to yourself. Sometimes you'll figure out when what you're thinking doesn't make sense when you hear it in a sentence. But the rate at which the oil is leaking is going down. But if I'm talking about the rate at which something's leaking, I say, oh, so leaking fast, leaking slower, it's still leaking. The oil isn't going back into the oil rig. Besides, that doesn't really make any sense. I've got a positive rate, right? So I'd have positive amounts of oil that have leaked over very small intervals of time. I might be able to estimate how much is leaked. So if I looked at a little tiny section of this graph right near where it was 28, maybe I say, okay, well, this is measured in days. So a little tiny section might be like an hour worth. So if it leaked for an hour at 28 cubic meters per day, I could do some unit conversions and say, oh, well, then this is how many cubic meters leaked during that time. If it's close to 28, I'd probably get a close estimate of what actually happened. So think about, and you have a graphing area to the right of this on there, if you want to sketch it there or if you just want to think about it. But think about if I were trying to track the total volume of oil that had spilled just since it started leaking. So total amount of oil spilled since it started leaking starts at, like the top graph on the previous page, starts at 0. See if you can imagine maybe a light sketch, what would this look like if I were to try to figure out how much total oil has spilled between time 0 and time 1 and time 2 and time 2. Like, think about the shape of this graph or some of the values. We'll do some more specific computations in a little bit. But think about if I were trying to graph the volume, not the rate of change of the volume of oil, what that would look like. This is what we're going to work on, being able to do, not the just drawing, but how would I make something that does this, that has this rate? What qualities would it have to have? Let's get this guy going again. Whew. Of course it does that. Didn't fix. So. Here's what GC says. Now, start at 0, 0. That seems like, okay, it has to start at 0 if it's the volume of oil that's leaked since it began leaking. Okay, 0's leaked if it just began leaking. If it was time 0, nothing's leaked yet. And I have numbers on my vertical axis. If you don't have numbers, then just not a volume of oil is leaking at a positive rate, then just thinking about, well, how could I come up with this at all? Say, well, sorry. I will get a better program, I promise. But starting from this time 0, 0 oil is leaked, that's for sure. And I know that for a while, I had fairly high positive rates. Now it's different rates all the time. It's not a constant rate. Because this graph isn't horizontal like the bathtub graph. It's not one rate all the time. But it starts out leaking, maybe leaking quickly, then leaking more and more slowly, leaking more and more slowly. The slowest it leaks is right around, what is that, time 1.3 days? So if I look and just see like, well, GC magically says this, we're going to learn how to do this. But I know that I'm leaking quickly and then more slowly and then more slowly. What is it about the shape of this curved blue graph that I could maybe look at that and say, oh, this is leaking, but it's leaking more and more slowly. What about the shape of it tells you that it's leaking more slowly? It's not a constant rate of change. Well, the slope, the steepness of it, what's going on with the steepness of it? Okay, it's changing. That's how I know it's not a constant rate. If it was a straight line, I'd say, ooh, constant rate of change in this accumulation graph, in this graph that's showing me the total volume of oil. So it's not a straight line. If it's not straight, it can curve different ways. Between time 1 and time 1.3, you can see, oh, this graph is pretty steep here. Would you agree it's less steep by 1.3? Yeah, less steep. So if I were looking at this, like we did the Usain Bolt graph, if I were looking at this and zooming in someplace around here and estimating slope, steepness, rate of change, so cubic meters per day, over small intervals, I'd probably get higher numbers here and lower numbers here, agree? Because if I look at small sections, this is a nice smooth graph, unlike the absolute value kind of pointy graphs that you've seen in some of the homework questions. When I zoom in, that looks more and more like a straight line, and if I had a sharper pen to write with, we could zoom in even farther and make it less of a length of time for the interval left to right, and make it look more like a straight line. Do those M computations and compare them. So I've got higher values of rate here and lower values of rate there, which correspond to, like higher values of rate here. So this is maybe position A here, whatever time that is, time 0.1 to 0.2 days, somewhere in that interval. I've got a relatively high rate of change. We didn't do any numerical computations to see why the Y value is like at 5 or something. And I've got a lower rate of change here. This looks closer to horizontal. Now, when we saw Usain Bolt's graph, it was never horizontal because he was running really fast the whole time, right? He slowed down a little bit at the end, but if you remember, it was slow to start and then got steeper and steeper towards the center of the race, and then at the very last, like the last half second or so, he seemed to slow down a little, like, yeah, I've got this one, doesn't matter, I'm not going to try hard anymore, I'm happy. Same sort of thing here. If I'm looking at this volume graph, this accumulation, how much has leaked, I can see the rate in it as being higher numbers and then lower numbers, and then, oh, it's a little higher again over at the end here, like comparing point A to point B to point C. If I look at small intervals over here, thinking about, all right, what's the rate like here? It's fairly high. This is one of the steepest parts of the graph right here. This is one of the lowest rate values, corresponds to one of the flattest places in the graph. And then this is a little higher than that, so this starts to get steep again. Or if you can see the curvature of this, this is curved downward while it's going uphill, meaning although there's more oil that's leaked, it's not leaking as fast as it used to be. Well, until we get to past this point B, at which point, well, it's leaking a little bit more. We better fix whatever mechanism it was that we're using to plug this because it's starting to leak faster again. Let's get this under control. But if you can just imagine thinking about the graph on the left and seeing those rates and then visualizing how that's going to affect the steepness or the rate of change. Now, these are all positive rates. So the graph on the right would always be going at least kind of uphill. It's relatively flat, hardly increasing in the center section when our rates are near zero. If I had other graphs where I had rates that were negative, doesn't make sense in the context of an oil spill here unless I was tracking how much was left in the tanker or something. But if I had other things where I had negative rates, my curvature could be interpreted somehow differently. But changes in the curvature, getting steeper and steeper versus getting less and less steep, can tell us things about the rate. And so we need to be able to go back and forth comparing rate graphs, which are maybe more new, because most of the time in the past you've probably dealt with constant rate of change, and that's very boring to look at those graphs. And then accumulation graphs, how much has happened because of that rate. So we're going to get a lot of practice at going back and forth, but let's talk about some of the specific computations. Like, how would I ever figure out what Y values show up here, meaning how many cubic meters of oil I have, other than it's going up steeply and going up less steep. That's kind of vague, but it's a starting point. And when you're looking at problems, you don't have to get everything understood instantly. Take your time, try to maybe visualize if it's something like this. Sketch yourself a graph. What sort of shape would this be? Or how would this be going upward? How would this be going downward? As long as you know what this is. In this case, it's oil. How would the volume of oil be increasing? How would the volume of oil be decreasing? Oh, it's not decreasing. It's increasing all the time. And start to piece together some bits and pieces about the question. So we're going to work on that. But, okay, first of all, again, the notation. We talked about this notation yesterday, but this says R with a subscript of V. R sub V of 0.7 equals 9.68. And that's something that's probably highlighted on your graph, maybe? No, not. But R sub V of 0.7 equals 9.68. So thinking about the input, output, independent variable, dependent variable, X, Y, whatever you want to call it, in this graph, I've got a point here. Here's some specific numbers to go with this. 0.7, 9.68. What does that say about the oil spill? Well, let's see. What is 0.7? What are the units on 0.7? Days. Okay, so at 0.7 days, there's something that corresponds to this. It says 9.68. What is 9.68 about? What units? Yeah, volume? Volume, yeah, rate of change of the volume, right? So this isn't 9.68 cubic meters of oil. This is 9.68 cubic meters of oil per day. It's the rate of change, or the rate at which the oil is spilling. In this moment, at the moment, the small interval of time, right around 0.7 days, 7/10 of a day, which is, I don't know, more than 12 hours, but I don't know. Don't know what 0.7 of a day is. But 0.7 of a day into the oil spill, this is the rate at which the oil is leaking. It's not an amount of oil, it's just the rate at which it's leaking. So if that were to continue for a whole day, in that next 24-hour period, in that next day, 9.68 cubic meters of oil would leak. But we know it doesn't keep that rate. It actually decreases after that. It goes back up a little bit, but never that high again. So this is just what I said a moment ago. At the moment, 0.7 days in this small interval of time, we can think of this as being an essentially constant rate. Like, imagine drawing a little tiny circle around it and zooming in. If I zoom in really close to this, maybe it looks like a constant rate. 9.68 cubic meters per day. Maybe I can use that for just like 1,000th of a day. I don't know how much 1,000th of a day is in terms of minutes and hours, but it sounds like a small amount of time. 1,000th of a unit on here. Maybe that's small enough to make this look like Oh, that's a constant rate there. So what does a constant rate look like again? Straight line how? Anyway? Horizontal. So somehow I have to zoom in on this, if I could zoom in close enough, and see it looks essentially horizontal in the rate graph in order to have a constant rate. So if I zoom in this far, doesn't look quite horizontal, agreed? But maybe, and let me move this guy out of the way, maybe not for this whole graph area here, but maybe, let me try my pencil, please. No, of course not. But maybe just right here. Maybe that's a small enough moment, right around 0.7 days, where within that little box, the blue actually horizontal and the red actual rate are pretty close, or maybe close enough so that I could say that during that moment, or in that moment, 0.7 days, there's an essentially constant rate of, well, I know that at 0.7, the y value is exactly 9.68 according to the graph above. So there is a point right there that has a y value exactly 9.68. This whole blue horizontal line is the line y equals 9.68. And within this box, not the whole graph here, but maybe for a little while, it's close enough so that I can say that during that small interval, 0.7 to 0.7005 or so, it looks essentially constant, essentially like this horizontal line. For a rate graph to be constant, for a rate to be showing a constant rate, keep in mind that needs to not just be any old straight line, this needs to be horizontal line, one constant y value, dependent value, because the dependent value is the rate. So, scoot this back out of the way again. If this rate of change in the moment 0.7 days is 9.68, let's do some computations. So I'm going to throw in some more numbers than what you just did on your quiz, but if I have a constant rate, we suddenly have a lot of helpers. How do I compute things? Oh, I can compute change over a small interval. I can compute the new final amount if I had a starting amount at the beginning of this small interval. Or I could even write a function for a way to describe the amount as it changes throughout the interval. So I could describe a function that applies to only this small section here that would describe the volume of oil that's being added a bit at a time, and describe it for a full, whatever, 0.001 day. And then have another one for a different 0.001 days, and have a lot of functions with slightly different rates. So looking at what this says over here, suppose that V of 0.7 is 13.15 cubic meters, meaning this is V, not R sub V. So this is the volume of oil at time 0.7, or in the moment 0.7. I know the rate. It's telling me the volume, 13.15. So let me put a point on here. At time 0.7, I'm going to graph this function V. This should look kind of similar to what you just did on your quiz. Here's a point. Time 0.7 days into the oil spill. Volume 13.15 meters, cubic meters rather, of oil spilled by that point in time. But I also know at this point in time what the rate of change is, and it's essentially constant. I'm starting at this little blue dot over here and going to the right for just a little bit, meaning going forward in time just a little bit. So I should be able to say, oh, this is just about a constant rate. It's a constant rate of 9.68, not 70-something square feet per minute, but in this moment, my graph is going to be increasing at a constant rate, because it's oil spilling, of 9.68 cubic meters per day. So if I wanted to find, there are two things here. The first one says dx and dv. So x is what we're graphing here. X amount of time gone by in days, and v, which I can call it v or like v. I'm using v kind of both ways, both as the dependent variable and the function name. Not generally a good thing to do, but you'll know what I mean this way. So this is v, my volume going this way, and x, time this way. So volume of oil, elapsed time. We've got time in days, volume in cubic meters. So if I wanted to find the volume at time 0.7013, I can maybe see on this, if you see the scale on the bottom of the graph, 0.7013 is maybe about, here. I've got 702 over there, so 7013 is going to be closer to 0.701. But it's going to go uphill. Now, I'm going to kind of ignore those for a little bit. I'm just going to say, well, it goes uphill for a little bit. If I go forward in time a little bit, the amount of oil spilled is going to go up a little bit. In terms of labeling this, my dx and my dv, dx is the horizontal, dv the vertical, I'd have a new amount of oil by the time I got to the end. But what's just dx? If I go forward in time to 0.7013. Yeah, 0.0013. So it's a very small amount of incremental time in days added, or looking forward a little bit ahead. Now, I don't really know what 0.0013 of a day is, but it sounds pretty short. But if I go forward 0.0013 of a day, that makes sure that I'm looking at only this tiny moment when my rate is essentially constant at this 9.68 cubic meters per day rate. So my dx for this first one here would be 0.0013. dv, the additional amount of oil that's leaked, or the variation in the amount of oil throughout this tiny amount of extra time. dv, that's the change in the dependent variable. It's supposed to be mdx, right? We've got a constant rate of change, which if we look at small increments of time here, we've got a constant rate of change. So mdx, I just figured out dx, our m is 9.68. Now, I'm just going to write this as a computation, but dv here would be 9.68 times 0.0013. All right, so it's a small additional amount of oil that's leaked during this small move forward in time. So if I wanted to figure out what is supposed to be this y-coordinate here, how high is this actually supposed to be? What would I need to do to find the new volume of oil by time 0.7013 days? Add dv. Yeah, so it's my 13.15 plus dv, the dv that we just calculated here, this expression. So this is my 0.7013, comma, 13.15 plus dv. Just writing it that way to save sanity, but again, it's just, if we can say that we have a constant rate or an essentially constant rate, especially like this, we can look in a small interval and see that there's essentially a constant rate during that interval. We can estimate and get a pretty good estimate of additional dependent variable values by using our constant rate of change tools. dy equals mdx, and y final is y initial plus dy or plus mdx. So find just the dependent change or find the new value of the dependent variable. Both of those are possible if we have constant rates of change. All right, let me erase that and we'll do the second question. Actually, you'll do the second question. Take a minute, see if you can figure out dx and dv expressions for those or computations for those so that we can find v of, or the volume at time, 0.702 days. All right, so what's my value of dx? If I'm interested in finding this value, starting from, 0.002. So I'm going to go forward in time 0.002 to be at time 0.702 days. But over that time period, oil's leaking at an essentially constant rate still of 9.68 cubic meters per day. So what's an expression for dV? The amount of oil that leaks during this small interval, or the additional amount of oil that's leaking during the 0.002 days. Right, 9.68 times 0.002. I'm just going to write 0.002 since I'm onto the edge of the paper here. So if I wanted to find this new y value, figure out how do I plot that in the right spot so that it shows up where it should, I need to know initial value plus the new dV. So the v value I started at, 13.15, plus dV, right? So that's the new dependent quantity that corresponds to the amount of oil that's leaked by time 7.002 days. If I knew by time 7 days, by time 7.002 days, or no, sorry, I put my decimal places in the wrong spot. 0.702. There we go. By 0.702 days into the oil leak, we've got 13.15 plus dV, where this dV is mdx, 9.68 times 0.002, the additional amount of time since we last measured the rate. All right, so I hope that that part seemed kind of like what we did on the quiz, only it was over smaller intervals. There's like several minutes of mowing the lawn, well, maybe 0.002 days of an oil leak, but same general concept. We have a starting point. We have an increase in elapsed time looking forward a little bit so that we can use a constant rate. As long as it's a small interval, this constant rate applies, and I can find both the increase during that interval and also the new value of oil spilled by the end of that interval. All right, so what we're working on, we have a bit more formalization to get through, but the key to all of it is constant rate of change. So what we're going to work on next is what you see on the other side of your green sheet. It's how am I going to write out, not just for specific numerical values, what I do, but how would I express this in general? So there's going to be several steps that we're going to need to do in order to get an estimate. And then we'll talk about how we can make an estimate that's better. But if I know m, a rate in cubic meters per day, based on a rate function, then I can use this dV equals mdt. So just the incremental change during a small interval, I can figure out the change, converting from independent variable change to dependent variable change using this factor of m. And we can also find a new final y value, like we talked about. V final is V initial plus dV, otherwise known as plus mdt. So this all requires that we have a constant rate. So as we talked about at first, this red graph does not represent something that's changing at a constant rate overall. But just like we talked, if you look at only small sections at a time, you can imagine it's kind of a constant rate, or essentially a constant rate if you look at small enough intervals. So we're going to start out with a poor estimate, where I'm looking at intervals that are a bit too big, but this way, A, we can see them, and B, there's only a few of them. But that's what we just talked about. But suppose that for 0.3 days, 0.002 of a day or 0.001 of a day. Suppose it for 0.3 days, something that's long enough that I can see. Pretend that I'm going to use this rate at the beginning, which looks like about 28 cubic meters per day. Suppose I use that rate for the first interval, or if we're talking about any sorts of changes that happen in the amount of oil spilled, if I'm looking for times between time 0 and time 0.3. And then at time 0.3, I'm like, all right, well, clearly this estimate is getting to be off. I'm going to reevaluate because I want to know something about what happened a little bit later. What I'd like you to do on your graph, you have a graph that looks just like mine, only without the blue lines on it, on the other side of the sheet that has R and A piecewise function areas at the bottom. We'll finish that up on Tuesday. But what I'm doing by making this graph here is saying, well, we're going to pretend that these are good estimates. They're really bad estimates. But we're going to pretend for now because I can see it, and I know I can make a better estimate if I use smaller increments at a time, like 0.01 at a time or 0.001. But let's use 0.3. What I'd like you to do is draw this same thing. So every 0.3 days, what I'd like you to do is pick a value that's actually on the function, and then we're drawing a pretend rate function here. So this is constant. The blue function here is exactly constant for a while, and then it picks a new constant value and uses that for a while, and so on. So do that on your paper up through this bottom one here, which goes from 1.2 to 1.5. So what this allows us to do is pretend that we have a rate function that has just 1, 2, 3, 4, 5 different constant values. In reality, it's blending from one to the next and so on. But using these 5 constant values, I could figure out just about anything I wanted as an estimate, not a great estimate, but an okay estimate during the first 1.5 days of this oil spill. So we're going to get a more detailed graph in just a minute. I know it's going to just jump on me, so I might as well do it now. But if I were to explain this graph here, just with numbers, I could say it's approximately, R of t. Was it t or x? It was x, right? X was my variable. So if I wanted to explain R of x, this blue graph, with numbers, I could say, well, it looks like it's about 28 for the first section, and then it changes to something else. You know how piecewise functions work? We have different rules for different portions of the domain. So I'm just looking at this and saying, let's just look at numerical values for a minute. We're going to write something less numerical at the bottom. But it looks like about 28, meaning 28 cubic meters per day, just based on it's a little bit under 30, for the first 0.3 days. So this is for x in the interval 0 through 0.3. I'm leaving the right side open on this so that at 0.3 I'm going to pick a new value. And this one looks just to be about 20. Right? So 20 if x is between 0.3 and 0.6. Right? So 0.3 is less than or equal to x, less than 0.6. And so forth. So I'm just going to kind of jot this on here, but this is about 28. This is about 20. And for each of these pieces, I'm pretending that this blue graph is what my rate graph is. This is it's an estimate. It's a poor estimate, but it's an estimate that we can at least kind of see. It's not microscopic little intervals. So this next interval, let's see, between 0.6 and 0.9, that looks like it's about at, what, 12 or so? If we're between, and I'm going to use interval notation this time, 0.6 through 0.9. And then I've got a rate in cubic meters per day of about, what's that, above 5, maybe 7. If I'm between 0.9 and 1.2 days. And then this last one looks to be just about, I don't know, maybe 3. But we have 5 constant rates in any case. So each rate applies in a different interval. And if I wanted to know, due to this oil spill, how much oil had spilled over the first 0.6 days, say, well, if it went 28 cubic meters per day for 0.3 of a day, and then 20 cubic meters per day for another 0.3 of a day, I just have multiple MDXs to work with. I've got different M's. So just as a thinking about how this is useful at all, if I wanted to know how much had leaked by time 0.6 days, meaning between time 0 and time 0.6, because we started at 0. Say, well, 28 cubic meters per day for the first 0.3 days as my estimate. So this is from the first interval, or using, I'll call it M1, my first rate times dx, my little increment here. So we're going to talk about some other sorts of notation. We'll have 2 different expressions for how much time has passed. But this is our rate times the amount of time that I use that rate, so our MDX. And then, well, I'm going all the way up to 0.6 days. Then there's some extra that's accumulating, but I'm pretending my rate suddenly changed to 20. In reality, it gradually went down to 20. But 20 times 0.3 indicates this MDX with a different rate. So I've got 2 full intervals that I used here. Hold on a minute. Please don't pack up. When you do that, it is hard for most of the people in the room to hear what's going on. I'll let you know when we're leaving. I'll leave on time, I promise. But first rate times the amount of time that I use that for, and the second rate times the amount of time that I use that for. If I want to figure out what's happened by this specific point in time, I can add these together. Now, I don't know what that actually is. 8.4 and 6. So 14.4. What are these? 14.4 what's? Cubic meters. Yeah, this is an amount of oil that's leaked. These are dV, the total change in volume from the beginning through time 0.6, came from adding up how much happened at one rate that I was pretending was actually this constant rate, but my actual rate is not that. And then what happened in the next 3 seconds when I used a different rate. Now it's kind of convenient to pick them every so often so we can have this nice regular pattern every 0.3 days. I'll just pick a new rate. Now let me ask this. This is 14.4 cubic meters of oil that leaked. This is my estimate. This is not slope cube, this is cubic meters. Do you believe that this estimate is an overestimate or an underestimate? Yeah, overestimate. Based on looking at what the rate we used was, the blue line, versus the actual rate, I know this is too high, but at least I have an estimate, someplace to start from. So we'll continue on Tuesday, but what we're going to do on Tuesday is build up how would I express this in general, not for just looking at a specific point in time, but in general for any t based on making a fake rate function, an estimate function. All right, that's it. See you Tuesday.